Bismillahirrahmanirrahim. Obtain the initial and final values of g of t if the Laplace transform of g of t is given by this function g of s is equal to s cube plus 2s plus 6 over s into s plus 1 square plus into s plus 3. So from the Laplace transform of a function, we can obtain the initial and final values of the function in the time domain, right? So for this we need to use the initial value theorem and final value theorem of the Laplace transform. So according to the initial value theorem, we can find the initial value of the function g of t. For example, at t is equal to 0 in the time domain, what will be the value of this function? So this is given by this limit here, limit s tends to infinity and s multiplied by g of s. So if we multiply this g of s with s and then take the limit, this limit when s tends to infinity, this will give us the value of the function g of t in the time domain at t is equal to 0. Similarly, the final value theorem, from this theorem we can get the value of g of t at t is equal to infinity, the final value of g of t. So at t is equal to infinity, the value of this function in the time domain is given by this limit when s tends to 0, s g of s. So we can apply these theorems to find out the initial and final values of g of t, right? So first the initial value. So to find out the initial value, we need to apply this theorem. We need to take this limit at s tends to infinity, and if we put s is equal to infinity here, so this function will be, the value will be indeterminate, infinity over infinity, right? So what we can do is we can transform this function. We can divide this numerator by this leading coefficient s, leading term s cube, and then we can similarly write the denominator also in the standardized form by taking the s common here and the s common here, right? So g of s, we take out this common s cube, so this will be 1 plus 2 over s square plus 6 over s cube, and this will be, this is s, already s there, and this is s plus 1 square, so we take s common here, so this is s square, this will be 1 plus 1 over s square, and this s common gives us another s here, and this will be 1 plus 3 over s, right? So we have s cube cancelled out with this s cube here, and we are left with one s only. And by this, so g of 0 is limit s tends to infinity, and we multiply this with s, so we have another s here now. So this s into 1 plus 2 over s square plus 6 over s cube divided by this s here, which is the leftover s, into 1 plus 1 over s square 1 plus 3 over s. So now we are ready to apply the limit, the initial value at 0, and this s cancels out with this s, right? So we now put s infinity. So when we put s infinity here, so 2 over infinity is 0, 6 over infinity is 0. Likewise, we'll get 1 plus 0 and plus 0, and in the denominator we'll get 1 plus 0 squared plus sorry, this is multiplied into 1 plus 0, right? So g of 0 is basically 1. So from the initial value theorem we get the value at t is equal to 0, right? At t is equal to 0 the value is 1. Now the final value, this was the initial value, now the final value. For the final value we need to apply this theorem, right? So we can simply put in the s is equal to 0 in the given Laplace transform, right? So g at infinity is equal to limit when s tends to 0 s g of s, right? So this is s multiplied by this s cube plus 2s plus 6 divided by s into s plus 1 squared into s plus 3, and limit s tends to 0. So this s cancels out with this s, and now we substitute the limit. So this is 0 plus 2 multiplied by 0, 0 plus 6 divided by this is 0 plus 1 squared into 0 plus 3. So that is basically 6 over 3, and so g of infinity is equal. So knowing only the Laplace transform, we have found out the initial value and the final value of the function in the time domain. We did not have the expression of the function in the time domain, we only had the Laplace transform, and yet we are able to obtain the initial value and the final value of the function in the time domain using the initial and final value theorems.